Finding the largest rectangle of ones in a binary grid is a common challenge, but checking every possible coordinate pair for a rectangle's quarters is too slow for large matrices. We can solve this by changing how we look at the grid. Instead of viewing it as a flat checkerboard, we can treat the ones as building blocks, turning the matrix into a histogram. Our strategy treats every row as the ground floor, calculating column heights to solve for the largest rectangular area row by row. This perspective shift simplifies the problem, allowing us to apply a fast one-dimensional array calculation across the entire two-dimensional space. To solve each row's histogram quickly, we use a monotonic increasing stack. This structure will store the indices of our histogram bars to track potential rectangle boundaries. As we move across the array, if the current bar is taller than the one before it, we push its index onto the stack. We are essentially building a list of bars that could still grow wider to the right. When we encounter a shorter bar, that growth is blocked. This triggers a pop from the stack, signaling that it's time to calculate the area for the bars we just passed. For each popped index, the height is determined by that bar's value. The width is the distance between our current position and the index now at the top of the stack. Multiplying these gives us the area. This stack approach ensures we only calculate areas when a rectangle's path is physically obstructed, allowing us to find the maximum area in a single pass. Let's apply this to a sample matrix. At the first row, our heights are simply the values we see, 1, 0, 1, 0, 0. As we move to the next row, we follow the reset rule. If a cell contains a 1, we add it to the height from the row above. But if a cell is 0, any column building above it is broken, and the height for that column resets to 0. By the third row, cumulative heights are 3, 1, 3, 2, and 2. What is the maximum area for this row? Processing it with our stack reveals a 2 by 3 rectangle. This gives us a current maximum area of 6. On the final row, the zeros in the middle columns reset those tall bars, significantly shrinking the potential area for the remaining cells. By tracking the maximum area found across all rows, we guarantee that we've identified the largest rectangle possible in the entire grid. This logic is implemented using two functions, one to iterate through the matrix rows and another to handle the stack-based histogram calculation. The matrix loop updates the heights array in place. This is efficient because we only need to store one row of data at a time as we move downward. Separating the stack logic into a helper function keeps the code organized and makes it easier to debug the boundary conditions of the rectangle. This solution runs in O of n times m time. We visit every cell in the grid exactly once to update our heights. Even though there are stack operations for every row, each index is pushed and popped exactly once, keeping the total work proportional to the number of cells. The auxiliary space is O of m. We only need enough memory to store the current row's heights and the stack, regardless of how many rows the matrix has. When a problem requires calculating rectangular boundaries across a grid, this technique allows us to reuse efficient one-dimensional algorithms by processing the matrix row by row. Connecting these two concepts, transforming two-dimensional space into a series of histograms, converts a complex area search into a problem we've already solved with linear stacks. Like and subscribe for more technical walkthroughs, and check the description for the full implementation.